Na realidade, eu vou falar inglês, porque eu acho que tem algumas pessoas de Argentina, mas pode ser que seja pouco melhor se eu falo inglês. Eu queria, em primeiro lugar... desculpa, sorry. So I will begin by making a short presentation of the event. So the event is called Geometries, because there will be several types of geometries along these days. And this event has been organized by IMPA and by the Université Joseph Fourier in Grenoble, in France. And this is supposed to be part of the Ano da France no Brasil, the Year of France in Brazil, which will officially begin on April 21st and end on November 15th. So we are a little bit ahead of schedule, but that's not so much a matter, at least for me. Okay, so in fact there will be three kinds of lectures. First of all, we will have mini courses, which will be given here at IMPA. And the mini courses essentially are about differential geometry and analysis. So they will be given by Gérard Besson and Hervé Pajot, two colleagues from Grenoble, and myself. So this will be today, tomorrow, and Wednesday. And then there will be conferences given in Grenoble by some colleagues, and they will be transmitted by video conference. So I keep my fingers crossed, just in case. So the lectures will be on algebraic geometry, a lecture by Jean-Pierre de Mailly, a lecture on complex and analytic geometry by Philippe Sidieux, and a lecture on arithmetical geometry by Emmanuel Père. So the lectures will be normally, if there is no trouble, at 9:30, 11, and 1:30 p.m. And then on Friday, there will be two lectures, again by Gérard Besson and Hervé Pajot. They will be given at the Catholic University in Rio. So for those who don't know, this is in the district called Gavea, and the street is Roi Marques de São Vicente, and the building is a big building right on your left when you arrive. This is called the Edifício Cardeal Leme, and that's on the 8th floor. And there will be posters here at some point. And the lectures will be at 9:30 to 10:30, and then 11 to 12. Okay, I would like to take just some time to explain that there will be also scientific activities. So this will be the second part of the event. There will be scientific activities in Grenoble, in France. So just so that you know where this is. So this is a map of Europe. The red part is the region in which we live. This is called Rhône-Alpes. So here you have some towns of Europe: Paris, Lyon, and Grenoble in black, so that you can see more or less where Grenoble is. It's not too far from Geneva. That's about 150 kilometers from Geneva, and about 100 kilometers from Lyon, so that's in the French Alps. And here you have some pictures of Grenoble. The first one is Joseph Fourier. That's the name of the university and also of the math department, taken from this scientist, which I guess everybody knows here. And then you have one picture of the city, so that's here. And the other pictures are in the mountain. That's not so close from Grenoble, in fact, but we have an outstation of a botanical garden. If you have time, that's a nice place to go. So, I mean, that's just to induce you to come to Grenoble sometime. So the scientific activities in Grenoble, there will be an international conference, Spectral Theory and Geometry, which is organized by Gérard Besson. And there is a summer school, so we have a summer school every year, and the topics of the summer school change every year. This year, the topics is optimal transportation theory and application, and one of the organizers of the summer school is Hervé Pajot. He is here, so if you want to have to ask questions, feel free to ask. And there will be posters of the summer school somewhere outside. So the university and the cooperation program between the region and the Ministry of Foreign Affairs in France, which is called Arcus Rhône-Alpes Brazil. Rhône-Alpes is our region in France. They will offer some fellowships. So there will be 3 fellowships for a 3-month internship at Institut Fourier. So this could be done essentially between May and November of this year, possibly next year. I mean, it depends on how things work out. And there will be 5 fellowships to attend the summer school. So the deadline to apply for the fellowships is April 30th. Application should be sent to me. On the site of IMPA, you have all the details for how to apply. And of course, I mean, feel free to come and talk to me or to Gérard or Hervé for this, if you want to know more about these fellowships. So here it is. So now I will begin my conference. Okay, so I will talk on spectral problems on Riemannian manifolds, and there will be essentially 2 parts. In the first 2 lectures, what I want to do is to give a kind of overview of what spectral geometry is. So there will be essentially older results somehow, but I think they give a nice view what spectral geometry is, at least spectral geometry of the Laplace operator, and one can really look at spectral geometry for other operators. And in the last lecture, I will give essentially an application, some application of spectral geometry, and this is also a very classical result of Doris Fisher-Colbury and Rick Shane, a positive result which, for example, allows us to prove that a complete stable minimal surface in R3 is a plane. So that's all very classical results, but I think that's interesting to see what the techniques are and the kind of results we are interested in. Okay, so let me go to the first lecture. So let me first give a short introduction to the spectrum. So I will be mainly interested in compact Riemannian manifolds. In the last lecture, I will talk about complete non-compact manifolds, but in the first lectures, I will concentrate on compact Riemannian manifolds, and the manifold may have a boundary. Of course, I mean, all the manifolds are supposed to be smooth. I mean, that's not written, but that's... Okay, so I'm considering the Laplace operator on these manifolds and the Laplace operator acting with functions. And so the Laplacian is given as the divergence of the differential of the function f. The Laplacian of f is the divergence of the differential of f. Well, sometimes I just mention the Riemannian metric, here G. And what the divergence operator is on one forms, so this is given like that. You use a local orthonormal frame. So this is given locally, but then you prove that this does not depend on the choice of the frame. And you take the covariant derivative of the one form, and then you take the trace of it. So you sum over the basis Ej of the covariant derivative of omega by Ej applied to the vector Ej. So if you are not so familiar with covariant derivatives of one form, what this means is that you take the one form omega, you compute the one form on the vector field Ej. This is a function. You differentiate this function in the direction of the field Ej, and then you have to make some correction. And the correction is just the one form which is calculated on the covariant derivative of the field Ej with respect to itself. And then you can easily show that this does not depend on the choice of the local orthonormal frame. and this gives you a function. Well, if you look at local coordinates, then the Laplacian looks like that. There is that's not so visible, but that's a red minus sign. Well, that's the geometer's convention. So I will keep with this convention, otherwise I will probably make mistakes. So I prefer to keep with this convention. So what you do is the following. You look in the local coordinates xj, and you look at the coefficients of the metric in these coordinates. So you take the gij below. So that's just the coefficients of the Riemannian metric in the local coordinates. And then you take the inverse matrix. So in fact, this inverse matrix describes the Riemannian metric on the cotangent space and not on the tangent space. So that's something on the cotangent space. And you have another interesting function, which is the square root of the determinant of the matrix Gij with the index below. And this function is just the density of the Riemannian measure in the local coordinates. Okay, so if you take these functions, then you have the expression up there. And well, something I should write, which is more or less obvious if you look at the form here, is okay. I will just write what happens if M is closed. So for me, closed means compact. Without boundary. Just not to write down the boundary term, but what you have is if you take two functions, so this is just by integration by parts. The scalar product of the two differentials in the cotangent space, and then you integrate against the Riemannian measure. And the minus sign is just to make this, to make no sign here. At some point you have a sign which must appear. Okay, so that's just the an integration by part. And if you look at the formula above, that's more or less clear that you have this formula, because when you integrate here against the Riemannian measure, you see that the first term cancels, and then you just integrate in the chart, and the formula is more or less obvious. So in fact, this means something interesting. I mean, this gives you two interesting things. Okay, I mean, if, let me just say this. If M is compact with a boundary, you have a boundary term, and you don't see the boundary term if you assume that the functions vanish on the boundary. Okay? So what this tells you, in fact, this tells you two things. The first one is that the Laplacian is symmetric. Okay, so let me write this. Again, assuming M is closed just to make things easier. And the second property is that the Laplacian is non-negative, which means that if you integrate f against the Laplacian of f, what you get is the norm of the differential, and this is non-negative. So that's two important properties of the Laplacian. And spectral geometry, first of all, we're interested in eigenvalue problem for the Laplacian on the manifold. Okay, so the eigenvalue problem is to find the the numbers, and in fact they must be real numbers, and the functions, we are only interested in non-zero functions, the pairs lambda u such that the Laplacian of u is equal to lambda u. And of course, if M has a boundary, you have to say something on the boundary, and I will assume that we consider the Dirichlet eigenvalue problem, meaning that we assume that u is 0 on the boundary. I mean, there is another problem which is called Neumann problem, but I will not consider this problem here. Okay, so if I don't say anything, then we look at Laplacian u is equal to lambda u, and if M has a boundary, then I will assume that u vanishes on the boundary. Okay, so the main theorem, and I will try to give some hints for the proof of this theorem. If we have a compact Riemannian manifold, then there exists a sequence lambda 1 less than lambda 2 less than or equal to etc. less than or equal to lambda k of non-negative real numbers with finite multiplicities. I will come back to that in a moment. And an L2 of M with respect to the Riemannian measure orthonormal basis, phi 1, phi 2, phi k, of real C-infinity functions such that the Laplacian of phi j is lambda j phi j. And if M has a boundary, the function phi j vanishes on the boundary. Okay, let me just explain what finite multiplicities means. Well, first of all, I have written this here. This is because, in fact, the first eigenvalue is simple. I will explain this later. And then I allow here two eigenvalues to be equal. Okay, so for example, we could have lambda 2 equals lambda 3 equals lambda 4, and then this is strictly less than 5, okay, than lambda 5, and so on. So what I want to say is that if the equality sign holds at some point, then this can only hold in a finite number for a finite number of eigenvalues, of successive eigenvalues, okay? So a given eigenvalue cannot have infinite multiplicity. It must have finite multiplicity, okay? But this can occur very far in the spectrum. Okay? And because it's not easy to control, it's better just to write down the eigenvalues, allowing the possibility for them to be equal to the next one. So now if you look at the set, sigma mg, that's the set of eigenvalues with the multiplicities, okay? Then this is called the spectrum of the Riemannian manifold, and Dirichlet spectrum if M has a boundary, and I put Dirichlet boundary condition. So the important thing is that this is a Riemannian invariant. Riemannian invariant meaning that two isometric Riemannian manifolds have the same spectrum. Okay, so now what is spectral geometry? Spectral geometry essentially addresses the three questions that are on the slide. So the first question is, given a compact Riemannian manifold, can one describe its spectrum? The second question is, what information on the spectrum can one draw from geometric information on the manifold? By geometric information, I mean, for example, you assume you have information on the curvature, on the diameter, on the volume, or on some Riemannian invariants, other Riemannian invariants, and how can you control the eigenvalues using this geometric information? And the last question, which I will essentially not address here, is what is called the inverse question. What geometric information on Mj can you draw from the spectrum? So this was, there was the famous questions in the, I think it was in 1963, which was asked by Mark Katz, and who asks, can you hear the shape of a drum. So this means if you have a drum playing in the room, and if you don't look at the drum, and you just listen to the sound and assume that you have a perfect ear, you can hear the exact pitch of the sound. Then can you determine the shape of the drum just from knowing the eigenvalues? Okay, so I will give one example later on. Okay, let me just, because I will need that later on, let me just give two examples. In fact, one knows very little about the first question. I mean, can one determine the spectrum? The answer is no. In fact, there are very few examples of explicitly described spectra. Here are two of those examples. The first simple example is the example of flat tori. So you consider a lattice in Rn, gamma, and you consider the dual lattice. So what I call gamma star, that's the dual lattice. So that's the point which I will call gamma star in Rn, such that the scalar product in Rn with any element of the lattice gamma, this must be an integer. Okay, so one can show that this, again, is a lattice. And then the spectrum is given as described here. So the spectrum if you consider the flat metric on the torus, the spectrum is the set of numbers which can be written as the squares of 4 pi squared times the squared of the norm of gamma star. Okay, and in fact you can describe the associated eigenfunctions. They are normalized so that they form an orthonormal basis. But the eigenfunctions are exponentials, and you see where the condition on of the dual lattice comes in is that if you add some gamma to x, then the product gamma star with gamma is an integer, and so you don't see this number, okay? So this is a well-defined function on the torus, and this is an eigenfunction for the Laplacian. Okay. So that's probably the simplest example. And now another example, which is a little more complicated, is the case of the round spheres. Here I have written only the two sphere because the formula are more complicated in general, so I will just write this. So the spectrum of the two sphere, the round sphere with the induced metric from R3, so that's the numbers k plus 1, when k varies in the integers, and the multiplicity of k plus 1 is exactly 2k plus 1. And in fact, one shows that the eigenfunctions are the restrictions of harmonic homogeneous polynomials to the sphere. So here are two examples. Then in general, if you know the spectrum of a manifold, of two manifolds, if you take the product of the two manifolds, then you know the spectrum of the product. Spectra of projective space are known. And well, spectra of some triangles are known explicitly. And that's more or less it. I mean, even if you take, you see, even if you take, for example, the disk in R2, well, the spectrum is supposed to be known, but in fact, the spectrum is given by zeros of Bessel functions. So that's not, I mean, you can give numerical approximation easily, but I mean, that's not fully explicit. And then if you take the hexagon, the regular hexagon, that's a very nice domain in the plane, and one does not know the spectrum of this. Oh, no, that's okay. Okay, so one does not know the spectrum of the hexagon, for example. Okay, so in fact, very little is known in terms of giving a full description of the spectrum. Okay, so somehow I will make a big jump, just because I want to introduce some tool for Gérard's lecture. So I will make a big jump, and I will go now to the heat equation, which in fact was used very early, and for example by Mark Katz in his 63 paper. He used the heat equation already. But okay, so let me just check the time. To talk of the heat equation, I will assume that the manifold is closed. Okay, so that's a compact without boundary. I will not consider the case of manifolds with boundary. Okay, so I assume that I have a closed Riemannian manifold, compact without boundary, n-dimensional, and we are interested in solving this Cauchy problem. So that's the Cauchy problem for the heat equation. So that's, we look for a function u of t and x, and we want the du dt plus Laplacian u equals 0. So the plus here is because my Laplacian has a minus. And then we want the function utx at time t equals 0 to be equal to some given function, say, for example, a continuous function. Okay, so one can prove that the solution utx is given by the following formula. So it's given by integrating, oops, the formula is wrong. So the formula is u. Okay, let me just write this again. And then the formula is u of tx is the integral over m of some function k txy against f of y against the Riemannian measure. Okay, so there is one f missing over there. And this function k is called the fundamental solution of the heat equation, or heat kernel on M. And it turns out that it is given by the following formula, that k of txy is the sum from I equals 1 to infinity of e to the minus lambda it, phi I of x, phi I of y. Okay, so lambda i's are the eigenvalues of the Laplacian for my manifold, and the phi i's are the orthonormal basis of eigenfunctions. Okay, let me see. Okay, so I think I have time to give some proofs. So we'll see if that works. Okay, so let me give a formal definition of what a fundamental solution to the heat equation is. So this is a function which is defined for t bigger than 0 and x, y in M with real values and with the following properties. So the function is continuous in the three variables. it admits one derivatives with respect to the t variable, the first variable, and first and second derivatives in the third variable. And I assume that these derivatives, I mean, the definition says that the derivatives must be continuous. And the function k must satisfy the heat equation. And then there is a condition, the last condition here, which tells you that if you take a continuous function, if you integrate this against k, and if you let t go to 0, then you must find f. And this essentially, this condition. So this can be written, this is usually written differently as follows, that the limit when t goes to 0 by positive values of, of k tx, this should be the Dirac measure at the point x. Okay, so that's the definition of the fundamental solution or heat kernel. Okay, so what one can do two things. The first thing is to prove that the heat kernel is unique, and then to construct a heat kernel. Okay? So how does one prove that the heat kernel is unique? Then there is this proposition which is due to Gaffney. So the assumption, as I said before, M is a closed Riemannian manifold. You take an orthonormal basis of eigenfunctions with eigenvalues lambda j. And the proposition tells you that if M has a heat kernel k, then the series here must converge for all t, x, and y, t strictly positive, and the sum must be equal to k of t, x, y. So this tells you that if k exists, then you know who k must be. And in fact, this tells you a little more, that if you look at this expression here of k, then you see it does not depend. I mean, you can switch x and y and nothing happens. So this tells you that the function k of t, x, y is equal to k of t, y, x, so the function is symmetric with respect to the space variables. Okay, so let me just explain how this is done. So the idea of the proof is as follows. So you have your function p of t, x, y. So let me fix t and x, and you take y as a variable. So this is in fact a C2 for t and x, y, t and x fixed. This function is a C2 function in the variable y. And so you can expand this function in Fourier series with respect to the orthonormal basis. So this is the sum from a equals 1 to infinity of sum fi of tx phi I. Okay, so this is in the L2 sense. Okay, and this is true for all t and x. And fi is just the Fourier coefficients, the Fourier coefficient. So that's just the integral over m of k of t, x, y, phi I of y. Okay, let me just write dy for the Riemannian measure here. So now if you take so here you have a function which is C1, in t, so you can take the derivative with respect to t. So this is dk dt, txy, phi I, y, dy. And now you have your assumption. I mean, k is the fundamental solution, so you know that this is minus the integral over m of the Laplacian with respect to y applied to k, txy, phi I, x, dy. So this is just because you see, this is because of equation 2 here. K satisfies this. So now you can integrate by parts with respect to the variable y. So this is minus the same thing, k t x y Laplacian. And then you can use the fact that phi a is an eigenfunction, and so this is minus lambda I, and then you recover this here. So that's fi of tx. Okay, so we have this nice relation, and this tells you that fi of tx is something e to the minus lambda it. And now if you use the third relation here, if you use the third relation here, and if you let t go to 0, you see that this, when t goes to 0, this tends to phi I of x. Okay, so this tells you that the constant here is just phi I of x. Okay? So if you go back to this expression, then you can write that this is the sum e to the minus lambda it phi I of x phi I. And again, I mean, that's a number, and this is a function, and equality holds in the L2 sense. Okay, so now this tells you that if you fix t and x, then you will have a subsequence such that the sum from I equals 1 to some big n sub I, that this converges almost everywhere to this function. Okay? So let me erase this. So this implies that for fixed Tx, there exists a subsequence such that the sum from, there is some sequence, e to the minus lambda I t phi I of x phi I of y converges almost everywhere to k of t x y. Okay, and now to conclude, essentially the idea is so let me remind you that we want to prove this proposition. So the idea is to conclude, you have to use Parseval relation. that if you take k of t x, k of t y, if you take these two functions and if you take the L2 product, then this can be expressed in terms of the Fourier coefficients. So this must be okay, so this tells you that in fact this series must converge, and since you know what the limit should be, then you know that the series actually converges for all t positive, x and y in M, and you have this nice expression. So somehow this tells you that if the heat kernel exists on the closed Riemannian manifold, then it's uniquely defined. I mean, it's uniquely determined. Okay. Well, something that we can see, because if you take here, you see, this implies that k txx is just the sum minus lambda I t phi I squared. And because this is a series with positive terms, you can just integrate in x, and then you have a nice function. Maybe, is it here? No. So there is a nice function. So now this tells you that if you integrate, then you find that this function, which I will call z, so this is just the integral over M of this. So this function here converges, I mean, this series converges for all t bigger than 0. And now, I will come back to this function later on. Okay, so this is, usually this is called the partition function. What happens, in fact, is what I will show you on examples is that this function carries geometric information. It's rather easy, once you know it converges, it's rather easy to see that knowing the eigenvalues with multiplicities or knowing this function is essentially the same thing. Okay, and this function carries a lot of geometric information. Okay, so I will come to this later on. So let me just proceed with the proof of the heat equation and keep control of time. Okay, so now how do we prove the existence of the heat kernel? So the idea for the existence is to go first to something which is weaker than the heat function. So the idea is to consider what is called a parametrix for the heat equation. So you see that's essentially the same thing I had before. If you just come back, you will see it's very close, except that here I don't ask dp dt plus Laplacian of p equal to 0, but I want this function to extend to a continuous function at t equals 0. So I ask less and more. A little less and a little more. Okay? And I keep the last assumption here. So that's what is parametrics. Okay, so let me just forget parametrics a little while. So now again, assume you have a fundamental solution. Okay, so if you have a given continuous function, yeah, then again there is a zero missing here. So take u0, a continuous function, and then you consider u of t of x is the integral of kt xy u0 of y dy, and this function solves the Cauchy problem. So meaning that du dt plus Laplacian u equals to 0, and the value, and here there is 1, 0. The subscript here is wrong. I mean, that's u. Okay? So let me write this properly. Just. So you take some u0, say a continuous function, and then u of tx is the integral over m of k of t xy u0 of y dy, and this solves du dt plus Laplacian u equals to 0, and u of 0 at 0 is just the function we started with, u0. Okay? Now if you play a little bit with the formulas, and if you consider this function, okay, so you take this function, but you integrate. So you define v of tx is the integral from 0 to t of u tau x d tau, with the more complicated expression on the right hand side. Now this function solves another problem, which is the inhomogeneous Cauchy problem. So this solves dv dt plus Laplacian v equals u0, and v at 0 is 0. I mean, I could add a term and put something non-zero here, but that's not important for me, so we'll just write this. Okay, so this formula is called Duhamel's formula. Okay. Okay, so this is this formula here. So now let me come back with my parametrics. P so assume P is a parametrics for the heat equation. Then it satisfies dP dt plus Laplacian P equals Q, where Q is some, say, infinity function which extends also to t equals to 0. And then the limit when t goes to 0 of P of tx is just the Dirac mass at x. Okay, and Q has this regularity. Now if you look at the difference between K, the fundamental solution, we assume it exists for a moment, and P, if you look at this function, P twiddle, then it satisfies this equation that the Laplacian of P twiddle, the derivative P twiddle with respect to t plus the Laplacian of P twiddle is minus Q, and at 0 it is 0. Okay, so if you, so it resembles this equation. Okay? So now if you play a little more, then you end up with this formula here. Okay, so there was a minus Q, so you put the thing on the left, and you end up with this formula. So if you assume that P is a parametrics, and you have a fundamental solution then there is a relationship between the two things, and this relationship is this formula, this formula here. Okay, this you can write a little differently. I mean, you have K, so you have the identity operator, and you have some operator which I call T, and T of A at Txy, I like it like a convolution, is Q convolution with A, and the convolution is defined by the formula, the last formula, okay? And then you can write that identity plus T applied to K must be equal to P. Now, and once you have this, of course, what you want to do is to say, well, if I know some P, then maybe I can determine K. So you write identity plus T applied to K is P. So this should be written as K is identity plus T minus 1 applied to P. And this, if everything goes well, then you know how to compute the inverse of this operator. And then you end up with this kind of formula. Okay, so you have a sum, the sum of a series, which is obtained by making convolutions with with Q, which is the heat operator applied to the parametrics. Well, this is, one has to do some work to see that, but that's not so complicated. That's essentially the idea. Okay, so now if we have a parametrics, then we know some way of getting hold of the heat kernel. So now, how can one get the parametrics? So to get the parametrics, the idea is to think in terms of Rn first. So what is the situation in Rn? Well, in Rn, with the canonical metric, we have a nice fundamental solution. Okay, that's very easy to check. So you have this. And now you think that, well, on the Riemannian manifold, if you are very close to a point, then you don't really see that you are in a Riemannian manifold. It's very much like Euclidean space. And then the idea is to say, well, I will try to make an approximation to get the parametrics. And here things are getting worse and worse in terms of computations. But so if you look, first of all, you write the first term, 4 pi t to the minus n over 2, and you replace the norm x minus y squared by the Riemannian distance squared. Okay, forget eta for a while, and then, of course, you know the Riemannian manifold is not exactly Rn, so you will find you will look for some corrections, some correction terms, u0 plus tu1 plus so on tk uk. Now, one of the problems is that the distance function is not smooth on a manifold. So somehow you have to keep, if you look at your product, m times m, you have to stay in some u, epsilon, say, the points whose Riemannian distance is less than epsilon, and you will choose epsilon to be smaller than the injectivity radius or convexity radius. Okay? And eta, essentially what you do is you take a cutoff function which is 1 near the diagonal, and then you cut off in such a way that when you multiply by eta, you don't see that d squared is not infinity. Okay? And now what you want is you want to find a parametrics. So here there is a subscript k missing. So the idea is you just apply the heat operator, And then you will define the coefficients U0, U1 inductively in such a way that when you apply the heat operator, the right-hand side is as small as possible with respect to T. You want to kill, in particular, you want to kill the singularities. Here you have a bad singularity, T to the n minus 2 when T goes to 0. So you want to kill the singularity, because remember that we want the function P, when you apply the heat kernel, you want the right-hand side to extend to T equals 0 as well, okay? So that's how you can find the U case. Okay, and at this point, it's, I mean, you have to read it for yourself. I mean, but I think that's roughly speaking the idea. So let me go back to the heat equation. So that's the way you prove existence. And that's interesting because somehow you control what you are doing. Okay, so there is a very abstract way of doing that. I will just write it for those who are familiar with spectral theory, maybe. I mean, you can write this operator like this, and here you have and you have to integrate in the plane. In fact, the spectrum of the Laplacian is here, and you have to integrate on the curve like that. And when you do that, I mean, you can define in an abstract way what this operator is. And then if you go to kernels, then there are ways here you can invert really this operator, and you can work like this. But somehow that's not so explicit. Okay, so I already introduced the partition function. So that's this function. Okay, so what I claimed is that this function carries a lot of geometric information. Okay, so let me show you why this function carries information. So the first formula is very well known. So this is the Poisson formula in a more complicated context. Poisson formula, usually you consider the torus Rn divided by Zn, and you don't see the dual because the dual of Zn is just Zn. Okay? So if you take any lattice and if you take the dual lattice, then you see that something happens, and Poisson formula can be written in this way. So you have essentially two sides. Here, where the sum extends over gamma star, what you have is essentially the partition function, okay, for the torus. Yeah, that's written over there. So you have the partition function of the flat torus, and this is the first expression. And the second expression, the second equality, is exactly Poisson formula. Now you see that well, this is a little bit misleading. I will explain you why this is interesting and misleading. This is interesting. This is interesting because you see at least two invariants of your manifolds. First, you see the dimension, okay, because you have this singularity, T to the n minus 2. So from the spectrum, you can see the dimension, okay, and you see the volume. Okay, you have two rather weak invariants, but you see these two invariants. Okay, then what is very misleading is that you have a lot of information in the other terms. You see, first of all, you have gamma equal to 0, so you have 1. And then you have terms with gamma different from 0, and you see that these terms are exponentially small when t goes to 0. Okay? So exponentially small terms, usually it's very difficult to see them. But here, because we have an exact formula, we do see them. And how can you interpret this part is just because the squared of the gammas, the gammas are just closed geodesics. I mean, the gammas, they correspond to closed geodesics on the torus. So what you see on the right-hand side are just the length of the closed geodesics. Okay, but unfortunately they appear as exponentially small terms. Okay, but here, because this formula is exact, then you get something. It turns out that you can do the same kind of computations for, in the hyperbolic case, if you take the quotient of h squared by some lattice, then there is a formula which looks very much like a Poisson formula, a little more complicated, which is called Zellberg's formula, which gives you the relationship between the spectrum of a hyperbolic compact manifold surface, say, with the length, what is called the length spectrum, the length of closed geodesics. Okay? So this is a nice formula, and it's misleading because in general we don't have that at all. I mean, that's true for flat tori, that's true for compact hyperbolic surfaces, but in general this is not, we don't have such a nice formula. Okay, there is another formula which is more related to what I explained just before, which is called the Meenakshi-Sundaram-Pleyel formula. So you have to learn how to pronounce it. After some time, you get used to it. And this tells you the following. This tells you when you look at this partition function z of t, it tends to infinity when t goes to 0. Okay? And this is, of course, related to the fact that the eigenvalues tend to infinity when lambda j tends to infinity. And then you have a first term. You have 4 pi t to the n minus n over 2 minus n over 2. So that's the same term as above. And then you have the same term as above. You have the volume. And you see there is a difference. Above, we have this first term, and then we have exponentially small terms. And here, we have terms which are essentially polynomials in t. Okay, this is true for, I should say, I mean, this is not so well formulated. I should say that for any k bigger than or equal to, say, 1 or 2, then there is such an expansion. Okay, there are numbers such that this holds for all k. Well, in fact, these coefficients, they carry a lot of geometric information. In fact, one can show that they are integrals of invariance, of local invariance in the curvature. So maybe I have to go back to my notes. Okay, so let me write this. So if you compute, I will just give you the first ones. In fact, the other ones are not so well known. So this is, so that's 1/6 of the integral over m of the scalar curvature. And the last one, the next one, just for to record it, I mean, that's something like this. That's twice. Well, of course, the coefficients here, they depend on the convention you make on curvature. So these numbers that don't really make much sense. What is important is that here you have quadratic polynomial in the curvature. The norm of the curvature tensor, the norm of the Ricci tensor, and the square of the scalar curvature. So that what this tells you, again, in general, what this formula tells you is that if you know the spectrum, if you know the partition function, then you know the dimension, you know the volume of the manifold. So we already saw that in the case of the torus. And then you know these invariants. And you see, for example, if you live in dimension 2, then you know the topology by Gauss-Bonnet theorem. So this tells you really some information on the manifold. Okay, and okay, I won't say more about that. That's very complicated, I mean, to compute these coefficients. One very interesting result, which is quite old, in fact, it goes back to 1910, something like this. It was not proved by the heat equation technique, but directly, is that this implies the asymptotic growth for the eigenvalues. Just before I mentioned that the eigenvalues lambda j tend to infinity when j tends to infinity. In fact, this tells you how they grow to infinity. They grow like j to the 2 over n. And this comes essentially from some kind of Laplace inversion formula. One can give a slightly different proof and probably simpler proof. Okay, so now let me come to what Gérard will need in his lecture. One of the motivations of his lecture. So I will now consider embeddings of a Riemannian manifold into a Hilbert space. And somehow what we want to have is a fixed Hilbert space. Okay, and the idea is to use the eigenfunctions. Now what is rather unpleasant, but we have to live with it, is that the eigenfunctions, I mean the eigenvalues, they have multiplicities. And even if they don't have multiplicities, you have to think that if you have one eigenfunction, then you always can take minus the eigenfunction. So you always have a choice. So here, this is also associated to the choice of an orthonormal basis of eigenfunctions of the Laplacian. Okay, so I do the following. I take a closed Riemannian manifold. I fix a basis, an orthonormal basis of eigenfunctions of the Laplacian, and I make this map from the manifold to the L2 space, the Hilbert space of real sequences, which are square integrable. And at the point x, I associate essentially phi j of x. I want to be in L2, so I put this e to the minus lambda j t over 2 in front of it. And then there is some stuff just before, so this coefficient here, which is not so important except for what comes next, but so you can choose, you can make a dilatation at some point. Okay, here I just consider j bigger than or equal to 2, because if I consider a closed manifold, there is the eigenfunction 1, say, or 1 over the square root of the volume, and this is not so interesting, so I just throw away this uninteresting eigenfunction. So we have this theorem. So you take a closed n-dimensional Riemannian manifold and an orthonormal basis of eigenfunctions. You consider this L2 space, and you put the canonical Euclidean product on this space. So the first claim is that for all positive t, this map, which is made up with eigenfunctions, is just an embedding from M into L2. Okay, now if you look at, if you keep in mind this formula, you see that there is a t to the minus n over 2. Here you see that I have a t. You should consider the squared here because you go into L2. So you have essentially a t n over 2. So this is to compensate the t minus n over 2 in the Meenakshi-Sundaram-Pleyel formula. And I have added some extra term here. So what happens is that when t goes to 0, in fact, the embedding shrinks to a point. That's not so nice. But if you look at the induced metric from the embedding, then this looks nice, because when you pull back the scalar product of the small L2, what you find, first of all, is the original metric. So that's an almost isometric embedding in terms of metric. And then you have some other term, which involves the scalar curvature and the Ricci curvature, and then smaller, even smaller terms, which we probably not know how they look like. So this is this is both a nice and not so nice embedding. Nice because here you see the metric from this embedding, and not so nice because the image shrinks to a point when t goes to 0. Okay. Well, how can one prove this this theorem? Well, the first part is rather easy. That essentially because the eigenfunctions of the Laplacian, they separate points, and so this gives you the embedding. And because they approximate smooth function nicely, you show that that this is injective, and then you show that this is really an embedding by looking at the differential, and this is because the C-infinity functions are well approximated by a series of eigenfunctions. Now the second part is rather hard computations, but the idea is essentially to use the same technique that I used to prove the existence of the heat kernel. So you will have these parametrics which depend on k, and then you can take k very big, and then you can show that you can differentiate. Not only you have this nice expansion, but you can also differentiate this expansion, and then differentiating the function u0 of x, y, then you can recover the metric. I mean, that's essentially the idea, but the computations are a little bit complicated. In fact, now I will give some other motivation for looking at such embeddings, and one other motivation is this. I mean, this theorem. Okay, let me explain this theorem, and then I will come to the motivation. So you see, let me try to explain what the theorem says. So the theorem considers the infimum of the Ricci curvature. So you are on your manifold, and you look at the Ricci curvature on the unit tangent bundle, and you look at the infimum of the values of the Ricci curvature. And you look at the diameter of the manifold. Okay, so you have two numbers. You multiply these numbers, and you look at some lower bound. And in fact, you write the lower bound in a normalized way. So n-1 is just because we consider normalized Ricci curvature, epsilon because we want to take care of sign of curvature, and alpha because we want to take care of the size of the curvature. Okay? And then what the theorem says is that if you take a manifold and you consider this bound on this quantity, the infimum of the Ricci curvature times the diameter squared, then there exists a real number which is essentially the diameter d of m times some number which depends on n, epsilon, and alpha. And he's not here, but I mean, if I want to please my colleague Gallo, I will say that this constant a of n, epsilon, alpha is explicit. I mean, we can compute it explicitly. That's not only that there exists a constant, you can actually compute the constant. So that's an effective theorem somehow. And then what the theorem tells you is that you look at the volume of M times the heat kernel of M on the diagonal, and this is always smaller than or equal to essentially the same thing on the sphere. But since the sphere is a two-point homogeneous space, you just can forget what the point is, and you can take this simple function, which is just the partition function of the sphere. And how you put the geometry in this is just by the number r. Okay, so you compare your the heat kernel of your manifold with the heat kernel of a sphere, except that the geometry is in the radius of the sphere. And the radius of the sphere is the diameter of M times this number, which only depends on the sign and size of the Ricci curvature. Okay, so yeah, I have to control time. Okay, I will say a few words on the proof maybe next time. What you can do when you have this kind of inequality, maybe I'll come back to that next time, but in fact you can get lower bounds on the eigenvalues. So this answers the second question I asked. If you have geometric information, can you get hold on the spectrum? For example, can you give upper and lower bounds on the eigenvalues? In fact, it turns out, I will explain this in the next lecture, it turns out that it's more difficult to give lower bounds than to give upper bounds of the eigenvalues. Okay? And here, what the preceding theorem says is that if you have this geometric information, a bound on the Ricci curvature and a bound on the diameter, then you can bound the eigenvalues from below. And what is interesting is that you have the same J2 over n, the same as in Weyl's formula. So somehow this tells you that this bound is good asymptotically. Okay, if we had another power of J, that would be so good. Okay, so this power of J is the right one. Okay. This also tells you something on the L infinity norm of the eigenfunctions, and this is essentially the second inequality. Okay, so let me now give another embedding. So you remember, let me come back to, you see I had this embedding by eigenfunctions with the e to the minus lambda it to have something which converges, and then I scaled the embedding to have a nice expression for the pulled back metric. Now I just forget the pulled back metric and I make a slightly different embedding. I just scale by the square root of the volume for homogeneity reasons. So again, that's an embedding. I mean, I just changed the scaling a little bit. And now you can consider this set of Riemannian manifolds. So you have the n-dimensional closed Riemannian manifolds whose Ricci curvature is bounded from below by some k, and whose diameter is bounded from above by some d. Okay, so that's a nice space of Riemannian manifold, and this was studied by Michael Gromov, who showed that this space, in some sense, is pre-compact. Okay, and what we wanted to do was to have a kind of analytic proof of this pre-compacity result. Okay, so so you introduce this bad-looking distance, which is not so complicated. So you see, what you do is you take two manifolds, and for each manifold you choose orthonormal basis for the eigenfunctions. And then you embed the manifolds in L2. And in L2, you look at the Hausdorff distance between the two sets. So you have a set like this, and you look at a tubular neighborhood of this set, and you say that the Hausdorff distance of the white one with the blue one is smaller than epsilon if the blue one is contained in the epsilon tubular neighborhood of the white one, and if the white one is contained in the epsilon tubular neighborhood of the blue one. Okay? And now, and that's the bad part of it, is because you have the choice of the orthonormal basis, then you have to play with the orthonormal basis. And that's why you have this infimum, supremum, and supremum infimum. Okay, so you want something symmetric, you want to get rid of the choice of orthonormal basis, and that's why you do this. Okay? Okay, so what you can prove is that this is actually a distance between isometric classes of Riemannian manifolds, and that with this distance, the space I mentioned before, this space is precompact. So this is an analytic translation of Gromov's theorem using the heat kernel. Okay, so I don't think I can really give the proof of this, but okay, I think I will stop here. So tomorrow, what I plan to do is maybe I will explain how one can get lower bounds using this. What is behind this theorem? I want to explain what is behind this theorem. Essentially, behind this theorem, we have an isoperimetric inequality, and what we use is isoperimetric inequality techniques to prove this theorem. So again, I mean, that's a little bit complicated to write things down, but I will at least explain what the rough idea of how one can get hold of lower bounds for eigenvalues using isoperimetric inequalities. I will try to explain this, and then how you can go from this to these bounds. This is rather easy. Okay. Okay, so do you have questions? Was that too fast?